Let's look at the quicksort algorithm for sorting an array of values. Note that my pseudocode is based upon that's in the Corman book on page 177. So quicksort consists of two functions. One is the quicksort function itself that receives the array A to be processed and the indices of the beginning and ending of the array. Then it's going to ask a question. If the first index is less than the last index, we're going to call the split function, which returns a value q, which will be an index into the array. And then we're going to use recursion to call quicksort again, this time processing the elements that come before q in the array A, and then also the values that come after index q in array A. So what does this function do? Well, the first thing we're going to do is we're going to choose the last element of the array for what we call the pivot. And that will be more clear here in a moment what that really means. And then we have a value I, which will be the index of the rightmost subgroup of array A of the values that are less than or equal to the pivot. That's what we're going to compare things to. And then the K loop will run through all of the elements, determining what the relationship is to the pivot. Are they less than or equal to the pivot, which means they need to be moved to the left side of the array? Or are they greater than the pivot, which means they end up, in the end eventually, on the right end of the array? And then we'll swap some things along the way. And then at the very end, this last swap here, we're going to put the pivot in its final position in this sorted array. At this point, we know its final position, but we won't know the others yet. And then we'll return the index of the pivot, which will be our Q over here. So let's see at a high level what I just said, and then we'll work through an actual example. So we have some array A, and we have these elements here that are unprocessed at this point. And we're going to choose the last element as the pivot. Now note that quicksort sorts in place. So ultimately what we're doing is we're moving things around within the array to sort the array. And then as we work through, we're going to treat the array. We're not having separate storage, even though I'm going to write it as if it looks like separate storage. But within the array, we're going to treat parts of it as three different parts. We're going to have the part of the elements that are less than or equal to the pivot. Then we'll have the part of the values that are greater than the pivot. We will have what's currently unprocessed. And then of course we still have the pivot. So we're treating our array as consisting of four subgroups, moving things around to go in the appropriate group. So as we move through unprocessed using K here, we will move values around. And the index I, which I said was for the index of the rightmost element of the less than or equal group. Here's the less than or equal group. So I is this rightmost element. Okay? And then once there's no more unprocessed elements, for everything other than the pivot, we know if it's less than or equal or it's greater than. What we do then in our array is that we would have less than or equal on this side in some order. They're not sorted yet necessarily. Then we will put the pivot in its final position, and then we will have the greater than values. And so how do we know where this goes? Well, if I know that there's three elements less than or equal to the pivot, and let's say the pivot, for example, let's say it was 7, and these three elements are, 5, 1, and 2, in some order. The order doesn't matter. But if I know there's three elements here, then the 7 has to be in the 4th position, right? And these have to be after the 7. It doesn't matter what their actual values are as long as I know they're greater than 7. And these values don't matter as long as I know they're less than or equal to 7. But I know if there's three of these, then the 4th position has to hold the 7, and all these values will be those that are greater than 7. So what do we do next? Well, then we return the index of the 7 in this case. We come back to here, and we call quicksort again. But now, quicksort only looks at these 3 elements, and the other call to quicksort, the second one here, only looks at these elements. So quicksort is a divide and conquer algorithm. The benefit in terms of cost is that if we get a split that's somewhat even, because I know these values are less than or equal to pivot, I also know that they're less than or equal to these values, right? Technically they would be, well, I guess if there's something here, they would technically have to be less than, but either of these groups could technically be empty. So if I know these values here are less than or equal to the greater than values, I don't need to compare to them. So I've greatly reduced the number of values I have to compare to each other. And likewise, if I know these values are greater than this group, I don't have to compare to this group, greatly reducing the costs. So let's work through an example to see how to actually do that. Now I'm going to write this as if I'm creating subgroups. But once again, remember that the way the algorithm works is it simply moves things around within the array. And so everything will still be stored in the array. I'm just going to make it look like there's a bunch of subgroups. So here's our original array, and we're going to choose the 5 as the pivot. Now there's 8 elements here, so that means the other 7 elements all have to be compared to 5. So we initially start off with, there's nothing in the subgroup that represents less than or equal. There's nothing in the subgroup that represents greater than. And then these 7 elements here, the 2, the 6, the 3, the 7, 1, 8, and 4 are all unprocessed. And then we'll have the pivot over here by itself. It never changes until the end. So now what we do? K would be pointing at the 2. Now 2 is less than or equal to 5. So our algorithm said to increase I, which is currently at index 0 if this is index 1, and replace these. Well, in this case, it basically just puts it back in the same spot. But conceptually, we think about it as going in this group. So once again, this is less than or equal group, greater than, and the unprocessed group now would be 6, 3, 7, 1, 8, 4. And we'll still have 5 over here. So now we look at the 6. 6 is not less than or equal to 5. So our indices move on for K, but that also means this technically is in the larger group at this point. So we have 2 here, we have 6 here, and we have 3, 7, 1, 8, 4, and 5. So what does our array look like at this point? So our array, so at this point, is just 2, 6, 3, 7, 1, 8, 4, 5. At this point, it's exactly what it was to begin with. So now we look at 3. Where does 3 go? Well, it goes in this group. So we have 2 and 3. Then we'll have 6 right here. 7, 1, 8, 4, and 5. So what just happened? Well, in order to put 3 over here, something had to shift. So what we did was we swapped these two. So the 6 went to this position and the 3 goes to this position. So at this point our array is 2, 3, 6, 7, 1, 8, 4, 5. Now technically what we did was the 6 went to the rightmost end of the group of values we know that are greater than, but since there was only one value there, it still stays in the same group. So now we look at 7. 2, 3 stays the same, but this group grows. And then we have 1, 8, 4, and 5. So our array is still this right here. Now we look at 1. So what happens? Well, 2 and 3 and 1 belong together. But what happens here? We need room. So the 1 needs to go over here, which means the 6 goes over to here. So that means now we have 7 and 6 in this order in this array. And then we would have 8, 4, and 5. So it means at this point our array is 2, 3, 1, 7, 6, 8, 4, 5. So once again, we swap these two. In order to put the 1 in the group that contained the 2 and the 3, the 6 took its place, which still puts it next to the 7, which puts it in this group. Now we look at the 8. So 2, 3, 1, 7, 6, 8, and then 4 right here, and 5. And now we look at the 4. It goes in this group. It's less than or equal to 5. So 2, 3, 1, 4. What happens? Well, the 4 needs to go right here. So the 7 goes over to here, which gives us 6, 8, 7, and the 5 right here. And so at this point, our array looks like this. 2, 3, 1, 4, 6, 8, 7, 5. And we no longer have unprocessed elements. So what do? Well, if we go back and look at our algorithm, it says now that we're done, what we're going to do is take, remember this was index I, what it said to do at this point is to swap what's at index I plus 1. So this is I plus 1 in terms of indices, swap these, which means that we will have 2, 3, 1, 4. Then we'll have the pivot. Then we would have 8, 7, 6. And so our final array at this point is 2, 3, 1, 4, 5, 8, 7, 6. Right there, which is what we have here. So as I said in the beginning at a high level, we know if there's 4 elements less than or equal to the 5, then the 5 belongs in the 5th position. And so now we would call quick sort on this, where the 4 would be chosen as the pivot. And we would call quick sort on this, where the 6 would be chosen as the pivot. So, unfortunately, both of these are on the end of their group. The 6 is the smallest. There's nothing less than or equal to 6. And there's nothing greater than 4. So these, from a performance perspective, would not be the best splits, but I don't have any choice on that. This is just how it worked out. But we'd work our way through. So what about performance in terms of that if we were analyzing it? So as I said, this is not our best case scenario. This, in terms of the splits, where we got 4 and 3, was what we would want for best case. But we can see for the subgroups, they're not the best case. But imagine they were. So if we're trying to find the big O value for the best case, what happens is that each call to split divides its subarray into 2 equal size parts. Okay. Now the particular values may be such that we can't get to, like we had here. Because we had 7 elements to split, we can't have 3.5 and 3.5. So in reality, my 2 equal size parts, I'm going to put in quotes to indicate they may differ by 1 element. So if we look at a recurrence relationship for that, since the cost T of n is equal to T of the ceiling of n divided by 2 plus T of the floor of n divided by 2 plus the cost for looking at the n minus 1 elements, which is big theta of n. So this is the cost for going through and moving the elements, but then we have to do the same thing for the 2 halves. So once again, the ceiling and the floor here to get, if we had, for example, 7 elements, instead of having 3 and 5 and 3.5, this would round up to 4, this would round down to 3. So if we were to pretend the floor and the ceiling aren't here, then really what we have is that t of n is equal to 2 t of n divided by 2 plus this. And the closed form solution, if you were to solve the recurrence, I'm not going to do it, but the closed form solution of this would be t of n is equal to n plus n log of n, that's base 2. This is the dominant term, so the big O value for this is n log n, or excuse me, n log n. That's the big O value for that. So that would be what we would have for best case. Let's see an example that would demonstrate worst case. This may surprise you, but imagine we have this. Already sorted. So how can that be the worst case? Well, let's think about what we have once again. We start off, or excuse me, this, I'm going to write this. This is less than or equal to group, which is empty. The greater than group, which is empty. Then we have the unprocessed values. 1, 2, 3, 4. And then the pivot. So I'll say unprocessed. And this is pivot. So what do we do? Compare 1 to 5. So that belongs in this group. Sorry. This is just 2, 3, 4. Compare 2 to 5. That belongs in this group. Compare 3 to 5. Belongs in this group. And we compare 4 to 5, and it belongs in this group. So we no longer have any unprocessed. So here's our index I. This is where this empty spot here would be I plus or plus 1. But because it's empty, that's really the same thing as this. Because here's our array at this point. 1, 2, 3, 4, 5. And we say put the pivot in the I plus 1 position so it stays the same. So what we end up doing then is that when we call, using recursion, when we call quicksort again, we have to process these 4 elements. There's no splitting of the work. Now all we did was get rid of 1 element. And so what happens then? Well, the 4 would be the pivot, so we'd be left with 1, 2, 3. The 3 would be the pivot, we'd be left with 1, 2. The 2 would be the pivot, we'd be left with just 1. So the recurrence relationship on this is this. T of n is equal to T of n minus 1 plus big theta of n. And the closed form solution is n squared plus n divided by 2. And so this is big O of n squared. So when the data are already sorted, we get our worst performance, strangely. So how could that be? Let's think about what's happening with the 2 cases. Okay? So let's say that n equals 8. So for best case, we start with 8 elements, and we split that into 2 quote-unquote equal-sized parts. So let's assume 4 went over to here, and 3 went over here, right? Because one of these will be the pivot, leaving 7 elements, and so 7 divided by 2 would be 4 and 3, if we round up and round down. Remove 1 element from 4 leaves 3. So we'll say 2 of these go on this side and 1 goes on this side. That's the closest we can get to split in half. When we have 3, remove 1 of those as the pivot leaves 2. So this really can be 1 and 1. And then this 2 needs to be split to just 1. One of these would be the pivot, leaving only one other element. So what about worst case? Well, once again, we start with the 8. Remove the pivot, but we saw that now we only have 7 elements. All went on one side. It doesn't necessarily matter. They don't all have to be the first or whatever, or the last. You could, as long as you just have one element that separates everything else. And then what would happen here? Then we'd have 6, 5, 4, 3, 2, 1. So the tree height here is the floor of log of n. Right, 1, 2, 3. You can see 3 levels here. What's the tree height here? N minus 1. So the dominant term here is n versus this. And then we have a cost associated with each of these. So if there's a cost of n associated with each row, that's where we get the n log n. And here we get the n times n minus 1, which is n squared minus n. That's dominant. That's it right there. That's basically the way it works out. So that's best case and worst case. What about average case? Turns out analyzing average case is somewhat challenging. Okay, so I'll let you consult an algorithms book for that to see the proof. But what they'll show you typically is that the cost is approximately equal to 1.4 n log of n on average, which means big O of n log n, just like in our best case. What this means, the 1.4, is that there's about 40% more comparisons. So why is this the case? Well, in terms of intuition, let's say we have this. Let's say we have 8 here, and initially we get a bad split. So I get 7 here, so we'll see this is a bad split. But then maybe for the next one, we get something that's somewhat okay. So let's say we get 4 and 2. Not quite as good as we might want, but it's not bad. Okay. Split. Pretty good. And let's say this one then becomes 2 and 1. And this just becomes 1. And then this has to become 1. So 1, 2, 3, well, it's 4 instead of the 3 we had before. So basically what happens is, and this is a good split for each of these. Basically what happens is, if we have enough good splits to sort of offset the bad splits just become a multiplier on our n log n. Let's say it doubles it, because look at what happened here. Instead of getting one good split here to get to a certain level, it took us 2 splits to get down to this point. Basically what I had here. It's not exactly the same. Okay? But it's approximately the same. Okay? So it took us 2 times to get down to the same level. And so if that happens enough, you're not quite doubling here, but it's kind of like doubling n log n. And remember, when we have something like this, we have cost is equal to c of some function g of n, and this bounds above, so this is an upper bound. Then we say it's big O of g of n. So we drop this part out for this, which is sort of what we do here. So anyway, that's one reason why quicksort is still considered in general to be a very good sorting algorithm. One thing to note that you might have picked up on as we were working through some examples is that it's not stable. So because we're moving things around, imagine we had this, 1, 2, I'm going to call it 7 sub 1. And, 7, well, let's write it different this way. Let's say we have 7 sub 1, that's a 1, 7 sub 2, and 1 and 2, and we have another 7, we'll call 7 sub 3, which is our pivot. So we're comparing these. Well, eventually what will happen is we see the 1, and the 1 needs to go to the beginning. So what happens then? The 1 goes here by swapping with 7, 1. So we would have 7 sub 2. The second 7 is what that means. 7 sub 1, 2, 7 sub 3. Then eventually the 2 needs to go over here. So we would have 1, 2, 7 sub 1, 7 sub 2, 7 sub 3. And then eventually we don't have anything to process, so 7 sub 3 needs to go right after the last of the less than or equal values, which puts it right here. So we would have 1, 2, 7 sub 3, 7 sub 2, 7 sub 1. So what was the point of that? Well, let's think about it. If instead of these 7s, these had been names, and this had been, Smith Alex, and this was Smith David. If you were sorting, you would want Smith Alex before Smith David if you're sorting by last name and subsorting by first name. But by doing this, now I've took Smith David and put it before whatever this is and Smith Alex. So it's not stable. Okay? So that was the quick sort algorithm.